Morning, everyone. Thank you for joining us today here. And please welcome Steve Kingston and Milos to talk about the AI of where, unleashing the power of GenAI on geospatial data.
Thank you. Hi, everybody. My name is Milos, and here with...
I'm Steve Kingston.
So yeah, I'll introduce briefly myself. Today we planned about 35 minutes of content, and we'll have about 5 minutes near the end for the Q&A sessions, but also I'll be around a booth, so if we don't have enough time for any questions, you can find me around the exhibit area. So Milos, I'm engineering lead at Carto, which is a partner of Databricks, but I used to be a Databricks employee up until like a quarter ago, and that's where Steve and I worked together on geospatial and AI use cases.
So I'm Steve Kingston. I'm a geospatial data scientist at Ordnance Survey. So that's Great Britain's national mapping agency. And yeah, I'm hoping to reflect today on the use of spatial grid indexing and foundation machine learning models to sort of accelerate computer vision applications in the context of our public sector use case.
So a little bit of a scene setting. So this is a data and AI conference, but one of the things that, in my experience, I've noticed working with data for over the last almost a decade, it's that we collect data with a location, on a location, no matter which data point it is, and throughout our ETLs, sometimes the location gets forgotten, but essentially every data happens somewhere. Every data point we collect had a location at the moment of capture, and then depending on the use case, we sometimes emphasize it, sometimes we choose to ignore it. But one of the first times that I came across geospatial data was when I was working in a bank, and I got an Excel spreadsheet with some bank branches and their locations, and then their distances to the high street. This is basically, probably where everybody gets a first encounter with the spatial location data, which is, latitudes and longitudes, or northings and eastings, basically representing XY axis location. And that usually means point data. You have one point representing one data observation. The things get a little bit more complicated as we extend that. So we have these notions of raster and vector data, which rasters are more of like an image-based data, so you have a grid, fixed regular grid against an area, and then each pixel in that grid represents a location, and it's always offset from the edge corners of the imagery. And it's useful for capturing weather, for capturing elevation, for capturing many variables in a spatial context in a very regular way. And probably the most famous shape of a raster is satellite imagery. This is something that you would often find. It's an aerial imagery from the top. You have your red, green, blue values for a pixel, and then you can actually feel and appreciate that that's as an image. Vectors are a little bit different. They are a collection of points representing what is known as a feature. So you can have roads being represented as lines, or areas of interest such as postcode areas or county boundaries represented as closed lines. Finally, LiDAR is probably the most complex one from the perspective of frequency. This is a complex sensory data that appears in 3D, and it can be converted into the other ones. And across these four concepts, you pretty much permeate any use case in any industry, as long as there is a value of adding that spatial component. You can augment your data with it. On the other hand, the data itself, we're talking about, I think probably throughout the conference, you're going to see a variation of something similar to this slide, which is the maturity of the data and AI and how we are progressing towards these generative use cases. Spatial data, in that sense, shouldn't be any different than any other data point. It's just, it can be presented more visually on a map, but for all other intents and purposes, it is just data. So what we're trying to do with some of these use cases is push the GIS together with its data counterpart towards the modern predictive machine learning and AI enabled type of use cases. And to keep the promise from the title around generative AI, one of the things that we used in the use case is combination of large language models. But to set a little bit of a scene, so for the ones that haven't used large language models so far. You can think of it as a system that has a encoding for a large amount of context, and it's able to generate answers that are closer to the way the humans do. So like, you can think of it as a technology that's very, very able to fill in the blanks based on some probability that it learned. And that can be quite useful for bridging the gap between an end user and a system that's very specialized, such as GIS. So what we're going to show later is like, how can we bring some of that human interface into the use cases to make it easier to extract features and generate insight. And then, as a counterpart to the language models, we have the computer vision, and this is where we think about large visual models. A prime example of that was a segment anything model that was launched by Meta a couple of years ago now, and it's been really, really powerful because you had a model that's trained once and then can be fine-tuned and then segment other type of imagery, and whether that's oblique imagery, whether that's satellite imagery, it just gives you quite a breadth of ability in that sense.
Thanks, Miloš. So to just set a little bit of context to the applications that we'll show a little bit, I'll introduce Ordnance Survey. So as the National Mapping Agency of Great Britain, OS conducts surveying across Great Britain, capturing authoritative, accurate, up-to-date geospatial data from which we derive a range of products and services. And our market segments broadly span government, consumer, and commercial. And in the commercial space, we partner to support customers, particularly in the utility sector around water, energy, and telecommunications. The government market segment is by far and away the largest, and OS's primary public task in that space is delivering geospatial data and location insights under what's called the public sector geospatial agreement. So that spans multiple themes of data: buildings, land, water, transport, addressing over a 10-year period to the wider public sector. And OS's value chain spans positioning, data collection, all the way through to data production and publication. And primarily, most of the data is collected through manual survey, whether that be field survey or through desk-based edits against aerial imagery. So the flying program makes use of two planes which fly on a 3-year revision cycle and capture what is approximately 12.5 centimeter aerial resolution. So that's supplemented with higher resolution targeted capture, particularly for locations which are of greater interest to UK government and industry, things like notable major infrastructure developments, etc. In addition to the airborne capture, there's also a network of 200 field surveyors, and through the Local Government Association, OS has a role as a national aggregator and distributor of address and street data from local authorities. So the geospatial production is primarily based upon the translation of aerial imagery into multiple digital representations. And there's a number of photogrammetry workflows which create a series of derived data products from this aerial imagery. So point clouds, digital surface and terrain models. And broadly speaking, those processes analyze the overlap between the image frames. And to also give a little bit of context to the data architecture evolution that we're undergoing as well. So traditionally, a lot of these digital representations are quite cartographic in nature, but we're looking more and more to adopt more of an object-centric data modeling approach, which is looking to better convey sort of the context and meaning which is understood by human perception. And so by adopting that object-centric approach, the aim is to create data which better represents the complexity and richness in the real world and hopefully leads to data which is more useful, usable, and supports a wider range of use cases. And geospatial innovation really underpins OS's capability to meet its customers' needs. And OS customers are asking for a lot more than just a base map today. So the data that OS collects really needs to evolve to support a greater diverse set of use cases and particularly advanced analytics use cases. And so to that end, just hold, go back one. Yeah, sorry.
Oh, sorry.
It's okay, no worries. So to that end, OS have been working closely with Databricks and Microsoft over the last few years around the cloud architecture and technology capability to underpin that delivery. And that's involved collecting all of OS's own data, as well as the data from partner providers, into a Delta Lake and migrating our geospatial processing to cloud compute using Azure Databricks. And the use of Azure Databricks has really brought an opportunity to rethink how we approach and optimize both the data and the approach to scaling that geospatial processing in the cloud. And the final point of interest that I'll call out is the interest in driving automation in data collection. So as part of this effort, we want to evolve what is traditionally very manual capture increasingly into automated feature extraction from imagery, as well as automated change detection. So driving change candidates, whether that's from comparing frames in satellite imagery, or it's by deriving broad land cover segmentation from an imagery and then comparing that with existing map data. And so Milos introduced Meta's segment anything model, and I think one of the great things about SAM is the adaptability to apply it to diverse image domains. And so to the best of my knowledge, the training data has little to no coverage of ortho imagery, so top-down imagery, but actually when applied in a zero-shot capacity, it shows real promise. And so there's definitely an opportunity to consider how to use this tool best to automate feature extraction and accelerate experimentation, prototyping, and validating use cases.
Yeah, and as Steve pointed out, it feels like a really good mix between technology and process, coming together, where something that used to, as you pointed out, was very manual. If you bring these new technologies, you can remove time and labor-intensive parts of the process, so you can focus on the quality of the outputs and the value of the outputs, as opposed to focusing on managing the time of the individuals and where they're going to be collecting the data. This way you can be very focused. Change detection will give you the ability to use those resources that are very expensive time-wise, so human resources, effectively. So you know where to go. Places where we detect change, that's where we want to resurvey. Places that are very stable, there's no need to resurvey and waste those resources. So it's quite powerful from that perspective.
So this slide shows an example application of actually what's called a language SAM model. And so it's worth calling out that one of the notable shortcomings of the base SAM model is the lack of support to segment by semantic properties or attributes. So there's been a number of developments which look to integrate natural language prompts. So in this example here, we have an integration with an object detection model, which through text-based input can define bounding boxes, which are used to prompt SAM to detect boundaries of objects in those boxes.
And to our opening point, it really brings to life the human interface brought into technology, because there is no code in this context. All we ask to the infrastructure is to give us trees. And in another use case, we could say, give us parking spots. In another case, it could be mark all of the rooftops, solar panels. It basically goes down to the path of my use case does not affect the infrastructure and the way that the system is organized, because its spine is there, it's well defined. The thing that changes is the question I'm asking it, but not how we deliver the answers. And I think on the far right, then it's a bit about delivering that. Given that these use cases are very spatial in nature, they're very map-oriented in that sense. The expectation from the consumers is that we can provide back to them a map, no matter if we generated it in a modern stack or not. And in that case, this is where a niche-specific type of technology needs to be mixed in. So if you were working outside of geospatial, that might be something specific to that industry. But within geospatial domain, we need maps. So once we extract all of the masks from the imagery, we can reverse georeference them, assemble the shapes, and then put them on in a data set that's indexed against a spatial grid. In the case of Ordnance Survey, that's the British National Grid. In case of a global data sets, that would be an H3 index system that's natively supported, for instance, within Databricks. And then on the other side is like, okay, so that's a really interesting use case, but how do we scale this out? As Steve mentioned, they have a full scan of a whole territory of United Kingdom of aerial imagery at 12.5 centimeters. Just to give you a little bit of a flavor of how dense and big that data is, Sentinel satellite data currently is available at 10-meter resolution. That's 2 orders of magnitude above of what we're talking here. So the smaller the pixel, the more data you actually are moving around and wrangling. And if you're applying a model, a very common size of a tensor is a power of 2. So we're talking either 256 by 256 or 512 by 512. So if you multiply that by 12.5 centimeters, we're talking about a single frame being 30 meters by 30 meters maybe, or less. And then you have to apply that against, well, I forgot the stat for the UK territories, 130,000 square kilometers. So it comes around 25 million images for one pass to just apply something. So you need to think about, how do I scale this? How do I avoid being stuck in front of the screen like it was the 80s, and then maybe I come tomorrow to see the results. So this is where the power of a platform like Databricks comes really to shine through usage of Spark, but maybe some other frameworks that are also available on the ecosystem. We can touch that later. And obviously, the very important ingredient is the way you store data. So what we leveraged here was Delta. It can be other open source formats such as Iceberg that's also could fit in the mix. The focus here is that it's a columnar storage where we can very efficiently store pieces of information that we need, and then we can very easily partition them and then make them act parallel. So you can send slices of data across a large compute and very easily scale. You don't pay more because what you pay for it is a number of seconds times the amount of resources. So if you scale it horizontally, the total amount of usage is the same, but you run faster. So it's very powerful from that perspective.
And so just elaborate a little bit on our experience with trying to scale using SAM. So once we have a nice, simple working example, you typically get to the point of, right, well, how can I actually deploy this model for batch inference over a larger data set? So we're talking maybe imagery which defines a citywide region, or even at the scale of a national run. And so sticking in the Databricks space, for vector machine learning, we'd typically use one of 2 options for sort of deploying a model for batch inference and prediction. So we'd broadcast a model and wrap it in a pandas UDF, or we'd use MLflow to create a PySpark UDF. So both of those approaches allowing you to make predictions on batches of data. But that approach actually we couldn't get working at all in this context, and probably speaks volumes of where the Spark processing paradigm maybe isn't best suited to the type of data in the model in question. And I put an asterisk on this slide because I have no doubt that someone with better Spark tuning expertise than myself might well be able to get it to work. But rather than looking at an alternative technology, we decided to try and make use of a new integration, so Rayon Databricks, as sort of motivated by the suggestion that this compute layer on top of your Databricks cluster provides really simple setup, as well as simplifying the way in which your data and resources are allocated in ML workloads.
And yeah, one thing that I would like to, for instance, reiterate on that is something that I came across when I was working for Databricks, because I was on a solution engineer side or solution architect side, which is the notion that Databricks is Spark. Databricks is a platform that provides you compute and governance and management of your data, but it's not Spark. So having something like Ray live on top of the Databricks layer is really natural, and this is where the suggestion came from, because we tried it with some other customers with very large models, and it worked well. And this is where potentially the angle from which Spark came to machine learning was traditional machine learning models, like you applying your XGBoost or logistic regression or similar things. Those are very compact models. We're talking a couple of megabytes. And that's on a large end. When we go into generative space, 2 gig is not a really large model, but it then starts putting burden on the infrastructure. Ray was built from another angle where they actually focus on how do we apply large models on top of a distributed compute. So it kind of has a little bit of advantages. To Steve's points, I'm sure that Spark will catch up, but it doesn't need to be one or the other. You have a flexible platform, you have tools at disposal, assemble things, build things, combine them. Use the platform as if it was a set of Lego bricks. There is no point to be too detrimental about using a single tool.
So what have we found? Well, I think, so one of the first observations was actually surprisingly there were minimal code changes. So broadly speaking, it involved creating a callable class which encapsulated the SAM inference logic. And then that class can then be passed to Ray's pool of actors via a map function. So that was the basis of the change. And the other really exciting thing was that moving from a CPU to GPU accelerated mode, again, was as simple as just defining a cluster with a GPU node type, and then making a few parameter changes in both the Ray cluster setup as well as the map function call. And so yeah, it's shown real promise and really impressive results with very little tuning. The other thing is that because you're working in Databricks, you get all the benefits of working in that space. So your sort of the support for Delta, as well as the use of Spark for perhaps pre and post processing of data. The one thing I will say is that it was a bit of a bumpy ride at first. I think because this is quite a new integration, there is a bit of a lack of substantial sort of documentation and examples. But yeah, I'm sure that again that will come in time.
And then I'm going to reiterate a little bit on the notion of combine things and integrate things, and divide and conquer, which is one of the basic principles in building software and building solution. As Steve pointed out, like scaling out the model inference and application, Ray. But then you have a wider ecosystem on Spark because it's more mature ecosystem. So you can think of preparing the data that can sit in Spark ecosystem. And for instance, what you see on this slide is just a subset of things that could be available within that ecosystem that are spatial in nature. And I'm going back to the notion of how we deliver this data was very important, because the people that would consume it, they had an assumption that this would be delivered as a geospatial data product. And the fact that we are generating it as a machine learning output shouldn't matter for them, because they're consuming it as a geospatial layer. So for that purpose, we can use any one of these packages, and probably another 50 are out there. I'm just giving few, common milestones such as GDAL. Mosaic was a package that we delivered through field initiatives back at Databricks. Sedona is an Apache Spark package that's been gaining traction. You can use those tools within this system without actually being locked into a single choice. And obviously, I have to mention Carto because this is where I work now. This is a way of, for instance, serving that in a very interactive way. So if you prepare the data in Databricks and store it in Delta, you can load it in a front end really quickly without having to use that burden of building your own front end application to serve spatial data. And from that perspective, this is another alternative. So what I talked on the previous slide is more like open ecosystem where you can pick up any open source package that doesn't come with a license. If you move into this like integration space, there are ISV solutions for you as well. So you can, in Databricks, there is like a partner connect part of the platform. So I invite you to check out there, even if not just exclusively to this type of use cases, but pretty much to any domain. There are partners out there that already have fine-tuned connections that can really accelerate what you can deliver. Within this domain of geospatial scalable processing on top of Databricks, what we're going to delivered through Carto integration is an enhanced wrapper around Databricks SQL together with Apache Sedona. And in addition to that, a layer of our own capabilities that you can call from your notebooks or from the integrated side. This is more focusing on that pre-processing and post-processing part where you're thinking about your outputs as data products that will eventually live somewhere, probably in a Databricks marketplace or another data product channel.
So I guess one of the things to think about in a distributed processing system is your indexing strategy. And I guess traditionally, spatial indexes use bounding boxes, and often they're implemented in like an R-tree structure. And that approach, you can use that approach on Spark, but typically it requires interaction with resilient distributed data sets, a lower level of data abstraction, and that's not something I enjoy doing. I think I wouldn't recommend that. And also, there's little support to persist R-tree indexing to storage for reuse in Delta and Parquet. So a different indexing paradigm is required. And to that end, as part of the collaboration, we've worked over the last couple of years on a strategy to index both vector and raster data. And the example here is about decomposing a geometry using the cells within a grid index system at a given resolution.
And one thing to just highlight here a little bit around the British National Grid, it sounds very UK specific. It isn't really. Most of the countries have their own national grid. So if you just abstract the B letter from the index system, it's basically a national grid. So I've supported customers back at my days in Databricks in the Nordics region. For instance, we are now in the United States. Every state has their own local projection. So it does allow you to actually index that area very efficiently. For vector type of use cases, H3 is really nice because it's very radial in nation. Hexagons are equidistant one from another. It forms a really nice structure. However, when we go into image processing, it's a little bit unnatural to have images cut into a hexagon. You can make it work, there is no problem with that, but a lot of other third-party tools expect square-shaped images where height and width are the same. So even rectangles would be a little bit awkward. So this is where the national grid systems are really useful because they are inherently based on squares. So that kind of fits the system of processing images at scale, and then pre-processing areas of interest into the square-based grid cells. So the joins are very efficient. You can very easily prune that imagery and then apply your logic, whether that's a model that scores an image, whether that's a model that extracts parts like clipping and segmentation that we already talked a bit about.
So this is the British National Grid, and this is the default coordinate reference system which Ordnance Survey collects and stores its data against. And since this was designed in 1936, and because it's been around for so long, it's really embedded in Great Britain's spatial data infrastructure. It's widely adopted in the community. And essentially, unlike a global CRS, it's sort of shaped and fitted to the landmass of Great Britain and sort of projects coordinates onto a flat and regular square grid. And I think, as Milos alluded to, I think the question about squares or hexagons or global or local CRSs or index systems, what I'd say is, I think if I was just focused on a data visualization use case, then the answer would be easy for me. I think there's generally a consensus that hexagons are more aesthetically pleasing, particularly pointy top hexagons. But when it comes to a spatial partitioning strategy, there's wider considerations. Primarily, your use case, the spatial distribution of your data, as well as I think thinking about data interoperability. So what data linkage do you want to support if you're going to be publishing data with index IDs, particularly thinking about the community. And so, yeah, just to very quickly expand why the British National Grid for us. Well, this image on the right-hand side shows the error expressed in meters where we reproject from British National Grid to, say, WC84 or the European equivalent, which is ETRS 89. And that reprojection is costly alone, but actually it's even more costly with the required reprojection grid. So that's called OSTN 15. And again, this isn't special to Great Britain. There's many of these transformation grids that you'll find across the world. And often they resolve the fact that you have differences in datums between coordinate reference systems, and they provide essentially like a matrix of reference points which are used to interpolate as part of the reprojection process. Yeah. And again, this slide sort of builds on an indexing strategy, thinking about a logical organization of raster data put into a medallion cloud data architecture. Now, I think we're probably stretching this a little bit because we've introduced a platinum layer on the far right. So yeah, you could argue that actually it's an oversimplification. But broadly speaking, I think the value release is in the materialization of indexes for reuse. So what we're looking at here is the gold layer where indexes available for anyone to go to. And in the Ordnance Survey, we've had real success with using Delta Live tables as a maintenance toolkit to index our most commonly used data sets and then to derive these downstream tables. I think it's also really important though to have a maintained store of in this case raster data which isn't indexed, but perhaps with common data architecture applied. So there absolutely will be use cases and consumers where the indexed representations don't work and they want to come back to the original source of data.
And one thing I would just add, I know that this has a very explicit geospatial nomenclature here, but if you go, for instance, in gold, we're talking here about indexed. The value of indexing your imagery is just because it speeds up a lot of your search needs. Just because in geospatial we have this very obvious notion of how to index, doesn't mean that this concept is not useful for any other imagery. So for instance, if you were to generate embeddings and add that as an additional explicit column to all of your imagery, you can then find nearest neighbors within that space that actually can help you quite a bit with defining errors, defining other types of transformations that you might want to do. So if the use case is more traditional computer vision that doesn't have a geospatial component, that this explicit indexing, it's still probably a very valuable idea that can help you better distribute and better scale out all of your processing. So it's something to reflect on.
So this slide shows a British National Grid indexing strategy applied to buildings and OS imagery. And I think just visually helps illustrate how having a unified data model with both vector and raster in the same index space is really powerful, where the grid identifier is your co-locating tool to just join these index components together in a really simple and streamlined way.
And then the real power, for instance, of this grid was to scale our joins. So what, for instance, can happen is, if you remember that first use case that we presented where we say, please segment all of this imagery and give us masks where you have detected certain concepts, such as parking spots, rooftops, trees, rivers, whatever. What the output of that is a vector layer. So what happens is if we index that vector layer, again in the same grid, we can join it back to the rasters and crop out imagery. And we actually had a very, very nice and easy to use implementation of that clip join logic within the Mosaic package in Databricks. And this is all the code you would need to take the outputs of a vector layer and go back to your imagery and just output all of the concepts masked. And how that visually looks like is something like this. These are, for instance, buildings. Oh, sorry, Steve. These are the buildings that were then identified with a specific rooftop. And then all of the rest of the imagery was masked, and they only then were presented in their identified areas, which is quite powerful because you can then start building new data products this way.
And so this is equivalent of that platinum layer on the far right as well. So I really like this as the concept of this being that you take your highest value vector features, so perhaps it's your buildings, it's your gardens, your sites, and you maintain pre-clipped raster data imagery, maybe digital surface models to those vector features. And if that's maintained over time, then you start to build up a temporal catalog as well of raster tiles relating specifically to features, which I think is really powerful.
And then there is, once you have that platinum layer, there is also a question of, how do we store it? I mean, we presented the bronze to platinum as a little bit on a high level. We didn't talk a lot about format, but there is a little bit of notion to capture is how do I store my spatial data in a way that it doesn't create a new niche. If you go out and do some research in the spatial domain, I think you have about 180 formats across vector and raster, probably more. It's a mess. And like that many options, it basically puts you in a paralysis by choice kind of situation. So we need to standardize a little bit, and we need to make some correct choices. So from that perspective, for vector data, one of the initiatives that's been alive for a while is GeoParquet. And before that, raises a concern. This is completely compatible with the vision of Delta and the vision of Iceberg and other systems, because it is just a specification of a schema that once the data is presented in that schema can be put into Delta, so you're perfectly fine. But it also brings all of the necessity of describing the vector data efficiently, so you can perform operations at a scale. On the other side, for the raster, there was a recent initiative that's been launched earlier last month for storing rasters as well in a Parquet format that will then bring a wider set of these data sets into a cloud-friendly location. And why is that important? Is for interoperability. We want to think of a wider ecosystem. So when you produce data in one system, you may need to use it in another, and you may need to bring it back. So having that storage layer well-defined helps you really with the integrations and doesn't lock you in. So just to illustrate how then that raster storage would look like, the idea is to then preserve those index grids, have each row represent a raster with its pixel values, so you can back export it as an image, but also store it as a native data types within a lakehouse. And then we explicitly will define the grid index system, so everything is also stored and it's compatible with your liquid clustering or Z-order or Bloom filters. But then add the ability to easily query that, which is really powerful. And rasters were not historically very accessible from the SQL perspective, but this does unlock that capability. And why is that important? Well, it's unification. You want to break silos. You want everything to be interoperable across your data estates, and you don't want to have a different system that has to be special to treat vectors, and then another system that's special and treats rasters, and another one that treats my traditional computer vision, and another one that treats my data analytics. Things need to converge and eventually be accessible to all of your data practitioners across your estate.
I think this slide just shows some examples in OS of where the value lies here. So, this type of approach supports everything from looking at the pitch and aspect of roof faces on buildings, to deriving building height, to looking at perhaps topological profiling of rural sites at the bottom. So it really is a diverse set of use cases that this approach supports. And we talked at the start a little bit about the use of SAM to accelerate proof of concept for computer vision applications, and without that extensive and laborious sort of labeled data collection exercise. Now, we'll just elaborate very quickly on the potential to fine-tune this as well. So in this slide here, we've got, we're fine-tuning SAM using a set of point data. So we talked about prompting using bounding boxes before, but these points can act as weak supervisors as well. So in this context here, we're looking at, well, can we fine-tune the model to maybe detect driveways, perhaps thinking about use cases like off-street EV charging capacity. And so before I show some of the results of that, the one thing I did want to mention is kind of domain-specific limitations. So I think it would be really naive for me to stand here and say that SAM's going to provide a solution for all your use cases. It's absolutely not. This is a really good example, I feel, of an OS requirement where we look to segment roof faces by their roof material construction. And so this supports primarily solar evaluation, but also things like emergency response. You'll see thatched roofs here. This is Dorset, a county in southern Europe where you find lots of thatched roofs. And often a hybrid approach is required, and there's no getting away from the fact that often, label data collection and a lot of technical investment and development will be required still. So this slide here shows the application against thank you, against a number of different spatial resolutions. So we're fortunate enough to have imagery at a number of different resolutions. And you can see here that perhaps the sweet spot is maybe somewhere about 8. And the next slide sort of talks about the trade-off. So the assumption being that higher resolution is always better. That's absolutely not the case. There's definitely factors to consider, particularly around data storage and management. And then finally, as well, it's worth saying that for certain use cases, using alternative viewing angles, so oblique imagery or non-standard imagery as well, has the potential to add value, but also comes with challenges, particularly around georeferencing and location.
And yeah, we're going to close with that. So I think my promise of giving you 5 minutes for question is completely broken, so sorry about that.
Yeah.
We had just a little bit too much fun. But yeah, thank you for your attention. And then we will be just outside of the room waiting if you do have questions to accommodate for those.
Thank you, speakers.